Hi, my name's Doug Dom.
And I'm James Witeska.
And today we'll be taking you through the FAE analysis and iterative design of the SB150 Yeti mountain bike on parts labeled A, the mainframe, B, the fork, and C, the brake rotor. Starting with the mainframe, we began with a very simplistic design that did not perform well under FAE simulations. The second iteration was much more complex. The third iteration included a slight geometry change to this joint, as well as a 30-pound decrease in weight. Here are the three next to each other. Note that the material is 1023 carbon steel. In the third iteration, there's 5mm thick walls, which is realistic to real-world applications. The tests for geometry optimization that we completed were resonant frequency analyses, as well as static analyses for jumping, sitting, and a rock hit simulation. The frequency analysis, the geometry changes to the frame increased the minimum resonant frequency up to about 400 Hz. This is concerningly low for real-world application because mountain bikes experience frequencies as high as 600 Hz. That being said, the suspension on a mountain bike is a complicated damping system that was not accounted for in this analysis. The first static test was the jumping/cliff drop test. The free body diagram on the right shows a fixture at the fork connection and a 1,000 Newton load that is appropriately distributed to points B, C, and D by the rear suspension. The table at the top holds the results for the three iterations undergoing this test. Note that despite a 50% decrease in weight from 60 to 30 pounds, in the second to third iteration, respectively, the max stress barely increased relative to the yield stress of 282 megapascals. In the sitting test, as seen in the figure on the right, is to simulate the weight of a 200-pound biker sitting on the seat. Unsurprisingly, the frame does not even come close to yielding under these boundary conditions. Finally, is the rock hit test. It's to simulate a 200-pound biker hitting a large rock with the front wheel at 30 miles an hour. Force A is about 5,000 newtons. This test had similar results to the jumping test with an increased maximum stress in the last iteration. Under the given boundary conditions, the part does yield in all versions, but it is worth noting that thanks to the front suspension, most of the force would realistically be dissipated. In this test, a nonlinear large displacements option was turned on for more accurate calculation.
Next, we'll move on to the fork arch. As shown, this is our original design. With our next iteration, we smoothed out some sharp edges from the original design, and finally, with our last iteration, changes to the arch included reinforcements as well as separate and rigid axle to wheel connections. Here's a brief summary of the design stage process for the fork arch. Note that our material of choice was magnesium alloy, for this material is primarily used throughout the industry. The test ran for geometry optimization included frequency, modal analysis, static and cyclic loading simulations for a jump, and finally a rock hit static analysis. Modal analysis was conducted on the fork. With each iteration, the lowest resonant frequency increased as planned. Note there are no boundary conditions in the study, and thus only modes 7 through 12 were considered. First, we'll talk about the cliff jump test, which was used to simulate a biker jumping off a cliff and landing directly on the fork, where 1,000 newtons was applied parallel to the fork arch. With the applied restraints shown in points B and C, the part did not fail in the final iterative design, as shown in the table. Next, we'll talk about the rock hit test analysis, which was used to simulate a biker hitting a large rock at about 30 miles an hour, where 1,000 newtons was vertically applied to the wheel's axis. The results show lower concentrations of stress from the previous study, and overall, the fork arch did not fail as well. Finally, a cyclic loading analysis was used to simulate repetitive racing conditions of a biker. As seen from the point on the SN curve, with the applied loads and restraints shown in the previous slide, the fork arch did fail due to fatigue. With that being said, with this fork design, an avid biker can still safely jump a cliff about 10 times a day for around 2.5 years before failure starts to occur. We did a closed-form analysis on the last two iterations using the same boundary conditions and loadings. The tables shown compare them to the corresponding FAE simulations.
Finally, we move on to the brake rotor. The first design of the brake rotor was a simple disc weighing about 2 pounds. The second design, we dropped some weight down to 0.8 pounds, and the third design, we increased in complexity and performance to about 1 pound. The first test that we did was a thermal analysis to simulate stopping from 30 miles an hour in 5 seconds. The heat power from the stop is 5,200 watts applied to the outer ring, and the convection coefficient of the wind moving past the brake rotor we decided was 500 watts per meter squared Kelvin. Note that the max temperature from these tests increased as iterations followed from 434 to 625 degrees Fahrenheit. Note that the real-world simulation should not use a constant coefficient of convection. The resonant frequency modal analysis yielded that iteration 3 performed better than iteration 2, but not as well as iteration 1. These results do not conclude a superior design. Finally, the brake rotor overall performance, the best in weight was iteration 2, the best in max temperature was iteration 1, and the lowest resonant frequency was best in iteration 3. Thank you for watching.